All right, so daily 2 number 1 is where a car is accelerating from rest. So v sub I is equal to 0. It accelerates at 4.2 meters per second squared over a distance of 36 meters. We want to know, we want to calculate the final velocity. All right, so we're going to use equation number 5 from our equation bank. V sub f squared is equal to v sub I plus v sub I squared, that is, plus 2 times a times d. All right, plugging your values in, 0 plus 2 times 4.2 meters per second squared times 36 meters. And breaking out my calculator, let's see, what do we get? 2 times 4.2 times 36 gives me an answer of 302.4. 302.4, but this is v sub f squared. So to get the answer, I need to square root this. So the square root of 302.4, and that will be to the nearest meter per second, 17. So 17 meters per second will be our answer there. Okay? All right. And then number 2 asks the question, give an example of an object that is moving in a negative direction and accelerating negatively. Well, I was looking at some of the responses, and people are responding with things like let's see, a car backing out of a driveway that is downhill. Okay, a car backing up is, it's kind of understood that it's moving in a negative direction. But accelerating negatively means it's speeding up in a negative direction. So if you're backing out of a driveway, that's great, but it would be better said a car going in reverse and speeding up, accelerating in reverse. Okay, so your velocity is increasing in a negative direction. Another really good example would be something that's falling, like a pencil. Okay, it's accelerating, it's moving downward, and it's accelerating downward at negative 9.8 meters per second squared. So a falling object is a terrific example of this. Or a car going in reverse, but I saw a lot of incorrect responses earlier, and here too, that says a car going in reverse but slowing down. That's actually incorrect. A car going in reverse and speeding up as your velocity changes from negative 1 meters per second to negative 2 meters per second to negative 3 meters per second. You're accelerating, your velocity is changing towards the negative. Okay, so that would be an example. All right, so a good example in the vertical would be something that is being dropped. In the horizontal, it would be a car going in reverse but speeding up in reverse. Okay. And be sure to note that speeding up part. If I ask you this on some assessment, don't just say a car going backwards. You know, you have to be a little bit more descriptive. Okay. All right, and that's the daily 2. Questions? No? Okay, well, what I'd like you to do, please, is to get out your work for Vector Form 1 that I asked you to turn in by today. And by the beginning of the class period, I want to go over the answers to those. Okay, so get out your work for Vector Form 1, and I would like to go over the answers. Okay, as I was looking at the answers and the responses, there were some people that were doing very well and some people that weren't doing quite so well. So, yeah. Now, I got a question in the chat window. Do we have to submit the work? No, not necessarily. Although if I see the work, then I can diagnose anything that you need to address, you know, individually. But that wasn't required. Okay, but I do like to see the work, and more on that a little bit later on. All right, so let's go over the answers to these. So I'm actually going to share the screen. I'm going to share the screen, and I would like to go through this little PowerPoint that I have. Okay, and here was the first one. Determine the resultant of 30 newtons at 0 degrees and 40 newtons at 90 degrees. Okay, so there's my starting point. I'm going to sketch it. So there's A and there's B, 30 newtons at 0 degrees, 40 newtons at 90 degrees. And my resultant is drawn from where we start to where we finish. Okay, and the magnitude of the resultant can be found by the Pythagorean theorem. So plugging my numbers in, my calculator gave me a value of 50 newtons. 50 newtons. Okay. Now, we also need to find a direction, and that direction will be this. Okay. It'll be this angle right in here. We always take the angle at the starting point. You know, sometimes people get a little confused. What angle do we take? We take the angle at the starting point, which is why I like to highlight the starting point with the little x. All right, now we know the opposite side and the adjacent side to that angle. Opposite and adjacent are related by the tangent function. Okay, so opposite over adjacent, and that's going to be 40 over 30, which is 1.3 repeating. Okay, and then using the inverse tangent button on my calculator, it gave me an angle of 53 degrees. All right. Now this if I put this on my reference compass up here, it's this. Now to get navigational bearing, we start at 0 and we increase by 53. Okay, 53 degrees is that angle right there. So the bearing is 0 where we started plus 53. We move in the increasing direction, 53. So that's the bearing. And then I report my final answer as 50 newtons at 53 degrees. Okay? Are there any questions about number 1? All right, let's go to number 2, where we have a plane flying at, excuse me for just a moment. I'm going to have to, oh gosh, I'm going to have to stop sharing. Okay, let's see if I can do that. And then I'm going to share the screen again. And let's see if that actually works. Get back to this. Wow, amazingly that worked really well. So I have a plane flying at 400 kilometers per hour south, and the wind is pushing it east. Determine the resultant magnitude and velocity, or determine the resultant velocity, magnitude, and direction. So there's my starting point, and it flies south, and then the wind pushes it east. So the resultant vector will be drawn like this. Okay. Pythagoras yields an answer of 408 kilometers per hour. Okay. And the angle that we're going to take is that angle right here. We know the opposite and we know the adjacent, so which are related by the tangent function, opposite over adjacent, 80 over 400. And taking the inverse tangent of that, we get 11 degrees. All right. And now transferring my resultant to my reference compass, that 11 degree angle is right here. Okay. And we started at 180, and we went counterclockwise. We decreased by 11 degrees. So we subtract 11 from 180. 180 minus 11, which is 169. So then my final answer, 408 kilometers per hour at 169 degrees. All right. Are there any questions about number 2? All right, then, oops, I'm going the wrong direction. I'm going to, okay, this is our next one. Number 3 on the vector form. We have two forces, 125 newtons at 270, 40 newtons at 180. All right, so let's find the resultant of these. So I'm going to go 270, okay, 125 newtons, and then from there, 180, and my resultant vector will be drawn like this, from beginning to end. Okay. Pythagoras yields an answer of 131 newtons for a magnitude. The angle that we're going to take is this angle right here, the one at the starting point of our vector triangle. And once again, opposite and adjacent are given. so we can use the tangent function. And my calculator gave me an angle of 18 degrees. 18 degrees. Okay? And transferring that to my reference compass, this 18 degrees was this angle right here. So I started at 270 and I went down. I went towards the smaller values. Okay, so I'm subtracting 18 from 270. And I get an answer of 252. So my final answer is 131 newtons at 252 degrees. Okay? Questions about this one? Okay, apparently not. We will get more practice at this. There was actually a question 4 on the Google form that related to this answer, but I'm gonna save that for another time. Okay, I'm gonna stop sharing and get my screen back, turn my video back on, and I'm gonna keep going. So, any questions? All right. Well, next, I want to continue talking about this, but I want to do a little application of this. So what I asked you to bring to class was a ball, and it could be a golf ball, a couple of pens, okay, and like a cup, a plastic cup. Let me show you what we're going to be doing with that, okay? I have that on my table here. Okay, now, I have a golf ball. Oh, you also kind of need a sheet of paper. You'll need a sheet of paper too, but I figured that was pretty easy to come by. Didn't have to go too far for one of those. So, all right, so now, I have a golf ball sitting here. I have this cup over here. My task is to make the golf ball hit the cup. So I'm going to push the golf ball. But what I'm going to use to push the golf ball are these 2 pens. Okay? I'm going to push 2 pens at the same time. Now the rule is my hands cannot go over the paper. I have to keep my hands on the outside of the paper. And I have to release the ball. They can only touch the ball when the ball is on the paper. When the ball leaves the paper, I have to take the pens away. Okay, so these 2 pens, I have to get them to work together to hit the cup. So, oh, no. Oh dear. That was a miss. All right, let's try this again. If you guys were here, you'd be pushing a bowling ball, 2 of you would be pushing a bowling ball with special sticks that I made, trying to knock down a pin. Okay, working together. All right, so let's see. No, missed. All right, let's see if I can do this better. Okay, so, that missed it anyway. I didn't push it hard enough. Okay, I'll try again. And I want you to try this with the ball that you have. Okay, push it with 2 sticks. Pens work good. And you got to keep your hands outside of the paper. Try to get them to work together. Hey, I got it that time. You got to hit the pin. Okay. Actually, I'm going to use one of this eraser as a pin. See if I can knock that thing down. Okay. So these 2 are going to work together to. Hey, I got it. Okay. All right. Now, what's my point of all this? Well, this is an example of something called concurrent forces. I have 2 forces that are acting on a point, on a single object, the ball. Okay, and these 2 forces combine to give a resultant force in this direction, right at my target. Okay? So these 2 forces, the ones from the pens, worked, and the resultant of those 2 forces are going to have a direction right towards my target. Okay? And this is kind of a fun thing to do when you're here, okay, pushing around a bowling ball with sticks. All right? Okay, so I invite you to try that with the ball that you have, a couple of sticks. And that could be pens or pencils, but the eraser tends to mess it up. So I like to use pens that have a flat top. All right. Okay, now, for a while, I'm going to be working with a document camera now, so I have to do a little setup here, so excuse me for just a minute. I have to a little bit of setup here. All right, and I have to okay. So now you can kind of see that up on the board. All right, my document camera, and I want to sketch this out. So what I have here, some paper. I'll need those pens. What did I do with them here? And the ball, which is way over there. Okay. So I have a. I have to let somebody in. Hold on a second. So let's say that this was where the golf ball was. Okay. Let's say this is where the ball was, and you can't really see that, can you? Okay. Is that better? Okay. Yeah. So this dot is where the ball was. Okay. And the two pens were acting on it and trying to kind of push it. They were more or less at right angles to each other, like this. Okay? Let me hover a little bit better. Now, instead of pushing them, let's say I'm going to put them on the other side. So instead of pushing, I'm going to move the force vectors over to here. Okay? And so we have a force going in this direction. We have a force going in this direction, and we have a force going in this direction. And they are more or less at right angles to each other. Get it up at the top. So now I want to draw this. So this pen more or less ended up right about there. This pen ended up right around there. And I want to draw some vectors. So I have a force vector that's trying to push the ball this way. I'll call that F1. All right. And then I have another force vector over here trying to push it this way. And I'll call this one F2. Now, these are called, when two or more forces act on a single point, okay, we call those, this is a vocabulary term, we call those concurrent forces. Okay, I will never actually test you on that term, but in case you see it, that's what they're, concurrent forces mean two or more forces that act at a single point, such as pushing on this ball. Okay, now, the net result, or the resultant of these two forces, was to have a resultant going in this direction, which we can actually find by adding these two vectors together. And the way we can add them, let me put these back. The way we can add them is basically by picking one of them up and setting it down so that we start the second vector where we finished the first. And this is the way we've been drawing the resultants up to now. There and there. Okay? First that way and then that way. All right, so I'm going to take this vector and basically pick it up and set it down here and draw it at the same length in the same direction. So I'm going to get the same direction by kind of laying my ruler down and trying to get it about the same. And then I'm going to make it the same length, and that's going to end up about right there. Okay? And so by taking this vector and moving it to here, okay, F2. Then we get our resultant is drawn from where we started to where we finished, right? Like this. That's by putting the tail of the second vector at the tip of the first one. And this is called the tail to tip method of adding vectors. And we get a resultant like this, which makes sense because the ball ended up moving in this direction. So, I have a ball here, and Bill tries to push it this way, and his friend Jill tries to push it this way. The net effect of Bill and Jill is to push it, along the line of the resultant. Okay? All right? Now, any questions so far? All right, now I'm going to introduce another way to add vectors. Okay? Let's take the same situation where I have excuse me for just a minute, where I have a point of concurrency right there, okay? And I have two vectors, same way as before, all right? So going there and going more or less there. So I'm going to draw this. That's going to be my F1, and F2 is right here. Okay. Now, I could add them tail to tip, as I did before. But here's another way that we can do it. What I'm going to do is I'm going to take this direction, the direction of F2, and I'm going to make it up here. I'm going to start it at F1, but I'm not going to draw a vector, okay? I'm going to draw just a dashed line. Excuse me for just a minute. Okay, my monitor computer went out. So, and I'm going to just draw a dashed line. Parallel to F2. And over here, starting at the tip of F1, I'm going to draw a parallel to F1. The straight edge, the ruler is pretty parallel. Dash the line. And they meet right here. Okay? So I make a parallelogram. I make a parallelogram out of the vectors. This is called, you see that? The vector parallelogram method of adding vectors. And the resultant is drawn from the beginning. It's a diagonal starting at the point of concurrency. And so that would be my resultant right there. Okay? Now, notice that it's the same resultant that we had before. Okay? It's the same resultant. But it's just drawn slightly differently. It's obtained in a slightly different way. Okay? Now, there's doubters. Why do we do it two different ways? Well, because they're convenient to different situations. If we have like displacement vectors, where you walk a certain distance in a direction, and then from there you walk in a different direction, it's more convenient to draw it like this, tail to tip method. Okay? But, and this is especially true for forces, when you have concurrent forces all acting at the same point, it is more convenient to draw them as all coming from the same point. And then we can add them by the vector parallelogram method. Example, if you stay in this, if you do a little engineering, okay, if you get an engineering class, you might end up talking about the truss of a bridge, that's going to have multiple points of stress. Right at this point of stress, you have 4 different forces coming in to this point. You have 3 different forces coming into there. And if we try to draw all those force vectors tail to tip, it gets very confusing. Okay, so we kind of want a different way of adding them. And so the vector parallelogram method is easier in those particular cases. Okay? Now, am I going to so now am I going to force you to do these? Ms. Towers, can I just do the tail to tip method all the time because that's the part I understand it a lot better? And I say, sure, yeah, go ahead. With more experience in physics, you will naturally see the advantages to drawing it this way, and you'll just kind of adopt that as needed, okay? But I'm not going to force you to, but you will see both of these. They're both valid. They're both equally valid, and one or the other is more advantageous in certain situations. Okay. Questions? All right. Well, I want to do another example then, and I'm going to have you help me with this example. And this is actually example number 5 on the vector example sheet. Okay? And I'm going to use the document camera for this. So if you don't have the vector example sheet, copy this down somewhere. We have a couple of vectors, okay? And the vectors are vector A, which is 50 newtons at 180 degrees, 50 newtons at 180 degrees. And the second vector is 25 newtons at 270 degrees. Okay, so if you don't have your sheet, that's fine. Just take this down. And what I want to find are the magnitude and resultant, or excuse me, the magnitude and direction of the resultant of these two forces. All right? Is it hard to see? Can't see? Okay, then what I'll do is I will just do this on the board instead of using the document camera. All right, so just give me a minute. Okay, I'll do this on the board instead. Okay, so let's see here. Let me turn the projector off. I don't need it anymore. Get some workspace. There's probably more workspace on here anyway. So what did I say? The first vector was the first vector is 50 newtons at 180, and the second vector is 25 newtons at 270. Okay, and I want the resultant of these. Now, as a visual, I want to put my reference compass here. 0, 90, 180, 270. I like to have that as a visual. So let's see, my first vector is going at 180, that's that way, and then 270 that way. So I'm going to have a starting point right here. And I'm going to draw my vector. That's going to be my vector A. And then my vector B, draw like this. Like that. Okay. Maybe a hair longer, trying to get it half as long as vector A. And this is drawing them from the same point. Now, if Bill wants to push the ball down this way, down, and Jill wants to push it to the left, the resultant is not going to be this. This is what I see sometimes, okay? All right, but if you keep your mind in the problem, you know, if Bill is going to push the ball down, Jill is going to push it to the left, the ball is not going to go in this direction. No, the ball is going to go both down and to the left. So we can, if we think about it, we can tell that the resultant of this is instead going to go like, oh dear, could have drawn that better. It's going to go more or less like this, okay? Which you also would have found, you know, I did this by the vector parallelogram method. If you pick up this vector, you add vector B to vector A, tail to tip, you're also going to end up here. Okay, so either way. All right, so we want to find the magnitude. And the magnitude can be found by Pythagorean theorem. So 50 squared, 50 squared plus 25 squared is going to be equal to the magnitude of r squared. And I happen to know this. 50 squared is 2,500. 25 squared is 625. So that's equal to 3,125 is the magnitude of r squared. But I don't know the square root of 3,125. Can somebody help me with that? What is the square root of 325? Chat window time. What is the square root of 325? To the nearest meter, to the nearest Newton, 56? Is that confirmed? Ronan got 56. Do we agree? 56? 56? 56, thank you. So the magnitude of R is 56 newtons. Okay, now, we want to take an angle, okay? We want an angle. Now, there might be some confusion as to what angle to take. Do we take this angle, x, or do we take this angle, y? Well, I'm here to tell you it doesn't matter, and I'm going to prove that to you, okay? And I'm going to prove that to you. Let's calculate both of them and see what we get. Now, angle x, we can use tangent because we know that vector A is 50. We know that vector B is 25. Because this is a parallelogram, this also has length 25. Incidentally, that length is 50 also. Tangent of x is opposite over adjacent. Okay. So, tangent of x, I'm going to write this in green. Tangent of x, that's the light green, I don't want that. Dark one, you can see it. Tangent of x is opposite over adjacent. And the opposite is 25, and the adjacent is 50. So, 25 over 50. Maybe it's easier for me to move the camera than the board. Okay? All right, 25 over 50 is 0.5. And then x will be the inverse tangent of 0.5. Calculators. To the nearest degree, what is the inverse tangent of 0.5? To the nearest degree. Ronan says 27. Do we agree? 27? Thank you. 27. So x is going to be equal to 27 degrees. Okay. Now, let's go back and figure out angle y. Actually, before I do that, if I transfer this, keep sliding this back and forth. If I take this resultant vector, transfer it to my reference compass, I'm going to get I'm going to get a resultant that goes something like this direction. Okay? Something like that direction, right? And then this angle right in here was 27 degrees. And then my true bearing, look where I drew that from. I started at 180. And I went bigger by 27 degrees. So my bearing, according to this, bearing is going to be 180 plus 27, which is 207. Okay? Now, what would we get if we used angle y instead? Well, I'll do this in purple. Where's purple? So angle y is right here. Opposite is 50. Adjacent is 25. So if I do that, then the tangent of y, opposite over adjacent, 50 over 25, which is 2. Y is then the inverse tangent of 2. Calculators, what is the inverse tangent of 2 to the nearest degree? Calculators, what is the inverse tangent of 2? $63. 63. So this angle is 63. But look where we started from. We started from 270, and we went down. We decreased by 63. So my bearing, in this case, if this is 63 degrees, that is 63 degrees, my bearing can be found by taking 270 minus 63. And 270 minus 63 is 207. Okay, so moral of the story, it doesn't matter what angle you use. You'll end up with the very same answer. You just do the math right. Okay? All right, anyway, my final answer then is R is equal to 56 newtons at 207 degrees. That is your answer. Okay. Any questions? All right. Well, I'd like you to practice one more for next time. All right. And so I'd like you to do this one for next time. Another couple of force vectors. We have, let's see, I'm going to say vector A is going to be, this is actually example number 6 on the example sheet, 120 newtons at 180 degrees, and vector B, 70 newtons at 90 degrees. So, please find the resultant, magnitude, and direction of the resultant of these two force vectors. Okay? All right. Okay, questions for me? All right. Okay. I want to give you the rest of the time to work on the answers to the collaborative test, the collaborative forces and Newton's laws test. Okay. Now, there were some students had some concerns about the work that they have to show when doing these problems. All right, and they were a little bit frustrated that I require you guys to show the work, not just in a couple of isolated cases, but I want to explain the reason why I do that. Okay. I need you to show all the work, and that's including all the equations you use when doing the problems on the written tests. And I have 3 reasons why. Okay. 1, you're going to use these. Reason number 1, you're going to use these tests to study for the final exam, or at least you should. And if you don't have a complete description and clear description of how to solve the problem, you could very well be really confused to the point where the tests don't help you at all. In fact, I was talking to a young lady who did pretty well on the individual test, very well actually, but in the collaborative test, she did not include the equations that she used, and I asked her, so what equations do you use? Did you use? And she she didn't know. She couldn't come up with them. And in fact, she came up with some ones that were incorrect. So if she had had those down, then it would be very clear to her. And then she had done this less than a week before. Just wait for a couple of months to pass. You're not going to remember exactly how to do these problems. You're going to need a refresher. And so you need a clear, understandable path from beginning to the end. The way I like to say this is you're not writing them for yourself or even for me. You're writing them so that you could give your test to an intelligent relative, your mom, your dad, your Uncle Billy, and they would be able to see exactly how you got the answer without you ever having to say anything. Okay? And so it is beneficial for you to have that down as a study guide later. That's reason number one. Reason number two, when you take physics at the next level at university, if you do, they are going to require you to show the work too. And if I let you get away with just showing, just give me the answer, that's fine, then they're gonna really take a lot of points off at the next level, and it's going to hurt you a lot more grade-wise than it will in high school. All right, so I'm trying to get you into good habits. All right, this is a college prep class. I'm prepping you for how they're going to treat you in college. Okay, and they're going to require you to show the work too. All right, so I want to get you into good habits. All right, so that it will help you versus hurt you later on. Okay, and that leaves then reason number three is the cheating issue. All right, when I was first discussing with my administrator years ago about how I would like to give half of my tests being collaborative or take home, so the kids will work together, my administrator said, "Well, Mr. Towdis, how are you going to keep the kids from just cheating, from just taking the smartest kids' paper, just copying down all the correct answers?" And I said, "Well, I thought of that. I thought a lot about that, and I can't. There's just, if I give everybody the test, I'm not looking over your shoulder. There's going to be, or at least it's open to the possibility that cheating is going to go on, where they take the smartest paper. Andrea is the smartest kid in the class. Everybody gets Andrea's paper, just copies down all the right answers, turns it in. Well, for number one, that's not very fair to Andrea, who did all the work, and it also doesn't indicate to me your level of understanding. And so, really, the test isn't worth the paper it's written on as an assessment, right? So, so I told my administrator, well, I'm not going to accept just the correct answer. Okay, they're going to have to show me exactly all of their steps in order to get the correct answer. And so that maybe, just maybe, even if they're just copying it down, maybe some learning is sinking in at the same time, So that's the reason also. So if you're going to cheat, I'm going to make you work for it. You're going to have to write down and have a very clear and easy path to the solution. You're going to have to write down everything. I'm not going to let you get away with just writing down the right answer. Okay? So that's my rationale. Okay? That's why I want you to show all the work. I thought about writing that in an email, but that would have taken me an hour to write to get all the wording correct. I thought I'd just take 5 minutes in class to do that. Okay? So, yes, it's a pain. Yes, Mr. Towdis, why do we have to do that? Well, for the reasons I outlined. Okay? If you have an issue, if you want to discuss it further, I invite you to come to office hours and talk to me about it. Okay? Not today because I have an appointment. I got to leave. But any other time. If you want to talk to me about something, do it, because that's actually good. I don't mind doing that at all, because it makes me self-examine. It makes me do it. Is that really what I want to do? Is it fair to the kids? And after thinking about this a lot, overall, I think this is the fairest way to do it. If you have a difference of opinion, then come and we'll talk about it. Okay? You might be able to change my opinion. It's happened before. All right? So feel free to do so. Okay. All right. So for the rest of the time, about 22 minutes or so, I'm going to send you guys into breakout rooms to work on the answers to the collaborative test. I would like these due by the end of the day next Wednesday. Okay? Make sure you put them in a different color ink, so I can tell new work from old. Submit them to Schoology again, and then shoot me an email to say you did it. Yeah, I'm going to have a lot in my inbox, but I don't care about that. The Schoology does not let me know when there's a resubmission. Okay, and I'm not going to go in and check every one. So just give me send me a heads up on that one. Okay. I can answer questions. Okay. If I said justify your answer, the correct answer with proper units is worth half the points. The explanation is worth the other half. Okay. For some of the problems. Sometimes the answer is worth even less than half if you have a whole lot to do. Okay, so it's not just the answer. But I've said enough about that. So if you have a question, then be sure to let me know and I can help. I will be happy to answer questions about this. All right, are there any general questions before we adjourn to breakout rooms? There will be a retake of the individual one as well that I have to write that. But let's do that next week, okay? If you want to retake your individual. All right, then. Well, off to breakout rooms we go. If you have a question, then be sure to let me know, okay? Okay. Aaliyah there. Kelly. Good luck, Kelly. Rooting for you.
Mr. T.
Yeah, question.
I got put into a different breakout room than with the people I'm normally with.
Oh, who am I talking to?
Same.
Who am I talking to?
Autumn.
Autumn? Who do you normally work with? Let me see. Hold on. Oh, I'm sorry. I'm going to send you to the right one. I didn't see your name there. I didn't see your name there. My bad. Okay. Was there somebody else with that same issue?
Callie also said that she was put into the wrong room. Yeah.
Callie. Oh, yeah. Sorry. Oh, gosh. My bad.
Thank you.
Yeah. Sorry. I'm going to turn off the recording.